Okay, next sample problem. I'm actually going to go through this one with you. Nice long one. But we actually go back to some of the older lessons. All right. So let's look at the question first to figure out what it is from the previous lessons that we're actually needing to go back to. As geologists study the area where an ancient marsh was located, they discover an unknown gas seeping from the ground. They collect a sample of the gas and take it to a lab for analysis. Lab technicians find that the gas is made up of 80.0% carbon, 20% hydrogen. They also find that 4.60 grams of the sample occupies a volume of 2.50 liters at 1.50 atmospheres, and it's at 25 degrees Celsius. What is the molecular formula of the gas? So right now, we know that this gas is made up of carbon and hydrogen. We need to find the actual molecular formula. We need to find out what those numbers are going to be. But we know that 80% of it is carbon. The remaining 20% is actually hydrogen. So let's look at some of the givens. Pressure, 1.50 atmospheres. Volume, 2.50 liters. Mass of the gas that was actually collected, 4.60 grams. R is 8.314 kilopascals liter per mole per Kelvin. And our temperature is 25 degrees Celsius. So, few things that we need to calculate. Few problems should come to mind. What are they when looking at these givens? The pressure. Notice the pressure here. Pressures in atmospheres, but our given are in kilopascals. Okay. And so pretty much that's really the most important one that you're going to need to change. So we have one of two options. We can change the atmospheres, right, into kilopascals, so we can just keep this constant, or we can change the constant. And the last lesson, I was saying that you want to change, you can change the R. I usually change the R value instead of changing my pressure, but that's up to you. The calculations I'm going to show you actually are where I calculate, I change my R value to include atmospheres. Okay, so let's look at, let's do that first. So we've got 8.314 kilopascals per liter over moles of Kelvin. That's really what that means, that number means, where the moles and the Kelvin units are in the denominator of this question. Now, I want to get rid of kilopascals. Where am I going to place kilopascals as a factor labeling? Pardon? In the denominator. That's where it's going to cancel it out. So that's going to do that. Now, we've gotten rid of kilopascals. What are we going to change kilopascals to? Atmospheres, right? That's really... Now, anyone remember what the actual conversion is? 101.3 what? So where are we going to put the 101.3? In the kilopascals, yeah. 101.3 kilopascals. 101.3 kilopascals is equivalent to how many atmospheres? One atmosphere. So in fact, we're multiplying it by 1. It's not going to make any difference. Right? So in fact, it's 8.314 divided by 101.3. So when we divide those two together, let me clear that and put the actual new R value. The new R value is 0.08207 atmospheres per liter moles of Kelvin. Okay, so this is my new R value. Okay, so It's my new R value. Now, we're going to put the idea of the gases aside for now. Right? Because ultimately, what are we really trying to find here? What value? If we think now of the gas law, the actual ideal gas law. We've got PV equals nRT. What are we going to try to find? Moles. Right? So we want to try to find moles. But first, what we're going to do is kind of go back to how to calculate empirical formula. Right? We know that 80.0% is actually carbon. Hydrogen, 20.0%. So we always look at, now going back to trying to find the actual empirical formula, we always assume a 100 gram sample, right? Because together we form 100%. So we always assume it to 100 grams then. Right? To a 100 gram sample. So how many grams would we say if we had a 100 gram sample would be of carbon? 80 grams. Right? So we'll keep the significant digits going. 80.0 grams. And how many grams will be of hydrogen? 20.0 grams. Okay? So we've got now the mass. What do you think we could find now of carbon and of hydrogen? For those who remember how to calculate empirical formula. We've got mass. The molar mass, right? So we're going to find the molar mass. Right? So we've got carbon and we've got hydrogen. So in this sample, right? In this sample, right, using the 80%, this is a hypothetical. We really don't have 100 grams of a sample. But we use that to help us find the empirical and ultimately our molecular formula. So we've got, hypothetically, 80.0 grams of carbon, and we've got 20.0 grams of hydrogen. So we're going to find the actual molar mass of carbon and of hydrogen. Molar mass of carbon, 12.01 grams per mole. Right? And molar mass of hydrogen, 1.01 grams per mole. Right? So, divide them. So what do we have here? The dreaded 6.66 moles is actually going to be carbon. And hydrogen comes out to 19.8 moles. So, we've got this. We've got the number of moles, right? And this is what we end up doing. To go back to, so, of carbon and of hydrogen, we've got 6.66 moles of hydrogen. We've got 19.8 moles of hydrogen. So what we always want to do, to find the empirical formula, we divide by the lowest mole value, right? Which is 6.66. Okay, so how many carbons in this empirical formula? One. Right? Which we usually don't put the one, but it's there. How many hydrogens? It's about 3, because I think it comes out to 2.97, right? So because of this value, because of this decimal value, we actually can round it off. Remember, don't round it off. Remember there was a chart I gave you guys mathematically. So please make sure you remember the actual values and which ones you can actually do. If it's between 0.95 to 2.99, you can round it off to the nearest whole number. So the empirical formula is CH3. Okay, so let's get rid of all this. Yeah, let's just get rid of it. I'll put back my R value in my equation. So remember, as we said, PV equals nRT. Actually, let's just put the empirical formula here off to the side. So we want to try to find now the number of moles in this sample. So we've got N is equal to PV over RT. Remember that my new R value was 0.08207, and now it's atmospheres, liters per mole of Kelvin. Okay, so we're going to substitute our numbers, and we can keep our pressure as the 1.50. So we've got 1.50 atmospheres multiplied by my volume, which is 2.50 liters. We're going to divide it by my new R value, 0.08207 atmospheres per liter mole Kelvin, and we're going to multiply it by our temperature, which actually we haven't. Oh, we did calculate it, right? No, we didn't. What was the other one? 298 Kelvin. Okay. So now let's look at what gets crossed out. Atmospheres, liters, Kelvin. Last unit standing are moles. So now the sample we've got here, the number of moles, or our N value, is 0.15333 moles. So this is the number of moles that we have for this actual sample. Right? We know the formula, the empirical formula, is CH3. We have the mass. So what we're going to do is we're going to find the actual molar mass. Molar mass is equal to the mass divided by the number of moles. So the mass, 4.60 grams, divided by our number of moles that we just calculated. So the molar mass that we found is 30.0 grams per mole. Now, what we want to do is we want to find the actual ratio between this molar mass, okay, and the molar mass of our empirical formula. Right? So what we want to do is we want to find the molar mass of CH3, right? But we've got the molar mass of the actual molecular formula of this actual gas, right? Which is 30.0 grams per mole. So I want to find this. Can I find that? Yes. Right? So pretty much find the molar mass of carbon, the 3 hydrogens, and we get 15.04 grams per mole. So we want to find the ratio, right? We want to find, what am I going to take CH3, what am I going to multiply it by to figure out what the actual molecular formula is? So what do you think I'm going to do with these two numbers? Divide them, right? So which order though? I can't just divide them the way they are, because I'm going to get now a decimal value. Right? 30 divided. I'm going to switch them around because I can't get. Remember, the smallest that this formula can be is what? CH3. Right? If I had a half, right? If I divided these the way it is, right? 15.04, and I divided it by 30, I'd get 0.5. So 0.5, I can't get a smaller formula than this. This is the smallest that my formula can be. So what I'm going to do is, I'm going to switch those two around. 30.0 grams per mole over 15.04 grams per mole, which is equal to, I got 1.99, but 1.99 can be simplified to a whole number of 2, which means CH3 is going to be multiplied by 2. So what is the formula of this gas? C2H6. So the the actual molecular formula is C2H6. Right, remember the molecular formula, and the empirical formula is the lowest coefficient that we could possibly get? Okay.